Dear students, this is our 25th lecture on organic reaction mechanism, and today we will be discussing quantitative treatment on effect of structure on reactivity. We know that the functional group present in an organic molecule influences the rate of the reaction, and this influence has been found to be in a uniform pattern, and this pattern has been shown to be quantitative in nature. So we can measure this pattern of influence in case of functional group present in the molecules. The empirical correlation which has been useful for quantification of this uniform pattern, this shows a linear relationship which involves logarithm of rate constant or equilibrium constant. For example, if we take the case of benzoic acid dissociating in water to give us a benzoate anion and hydronium ions. So here the rate of the reaction will be affected by the presence of, say, this substituent at the para position. Greater the value of equilibrium constant in this reaction, this will indicate that more of benzoic acid is converted into benzoate anion. So this substitution, whether this is an electron withdrawing substitution or electron leasing substitution, this will have a linear relationship with the rate of dissociation of benzoic acid. You can see over here the value of log K changes linearly as we move from electron withdrawing group to electron leasing group through unsubstituted group. So unsubstituted means when X is H, that means when we change from benzoic acid to electron withdrawing group substitution of groups like nitro, cyano or chloro, or electron leasing substituents like methyl or methoxy. So you can see over here the rate changes, the value of log K changes linearly as we move from electron leasing, electron withdrawing group to electron donating groups. Then this effect of substituent on para position, this can be explained by taking these two examples. One example is where we are having an electron donating group attached at the para position, and other is where electron withdrawing group is attached to the para position. And if we compare the value of K, then this K for unsubstituted, this will be less than K for nitro group, whereas this the value will be more for electron leasing group. So this is the reason for this change in value of K from electron leasing to electron withdrawing through unsubstituted benzoic acid is because of resonance effect. And for example, if methoxy is present at para position, and we know methoxy is an electron leasing group, so this will resonate through this ring in this way that this carbon will have a negative charge, and here also there is a negative charge, and same charge on these two positions, this destabilizes the resonating structure. So that is why here the value of log K will be more, because this has destabilized the system. Similarly, if we take the case of electron withdrawing group, then electron density will be attracted towards this electron withdrawing group, and you can see over here the resonating structure. Here this carbon now will be having the positive charge, which will stabilize this negative charge present on the carbonyl. So that is why electron withdrawing groups, they will have a stabilizing resonating factor, whereas electron leasing or electron donating groups, they will have destabilizing effect on these resonating structures. Now this whole relationship, which is linear in nature, was explained by Hammet, Louis Black Hammet in 1937, and his work is popularly called as Hammet Equation in organic chemistry. And this Hammet Equation describes a linear free energy relationship relating reaction rates and equilibrium constants for many types of organic reactions of benzoic acid derivatives, where we are having meta and para substituents present at the benzoic acids. And this Hammet equation is explained with just two parameters. One parameter is substituent constant sigma, and other is reaction constant rho. So relationship of these reaction rates or equilibrium constant with these substituent constant and reaction constant is known as Hammet equation. The basic Hammet equation, this relates the equilibrium constant. For example, this is the basic Hammet equation, that log of kx upon kh is equal to sigma rho, where kx is the equilibrium constant for the substituted benzoic acid, whereas kh is the equilibrium constant for unsubstituted benzoic acid, and this sigma is a substituent constant, whereas rho is a reaction constant. Then the value for the substituent constant depends only on the specific substituent x, that what kind of substituent is present, that is either at meta position or para position, that this whether this substituent is an electron leasing group or it is an electron withdrawing group. So depending upon the type of specific substituent, we will have the value for this substituent constant, that is sigma. Whereas in case of reaction constant rho, this will depend only on the type of reaction but not on the substituent used. So this is reaction dependent, where reaction constant is reaction dependent and substituent constant is substituent dependent. And similarly, this Hammet equation also holds good for rate constants also. The equation also holds for reaction rate K of a series of reactions with substituted benzene derivatives. So here also log Kx upon Kh is equal to sigma rho, same thing. So they are related to each other, whereas Kx is the reaction rate constant for substituted substrate, whereas this Kh is the value for unsubstituted substrate. Now Hammet equation, as I have told you, this is applicable only to meta and para positions. This is not applicable to ortho substituted aromatic rings because of the steric hindrance which arises due to the presence of any substituent group at the ortho position. So the steric and space effects, they show increased crowding in the tetrahedral intermediate. This tetrahedral intermediate which is formed during the reaction. So this presence of this ortho substituent shows increased crowding, and because of these steric reasons the Hammet equation does not hold good for ortho substituted substrates. Similarly, aliphatic carboxylic acids, they also do not obey Hammet equation. Here also there is a small increase in steric crowding in the transition state, and the flexibility of the substrate in the transition state also increases, which decreases the correlation between the transition state and the equilibrium. So because of these reasons also this Hammet equation does not hold good for aliphatic carboxylic acid. So Hammet equation is only applicable to aromatic rings which are attached to reaction centers at substituents with meta and para positions. The quantitatively the electronic effect of each substituent relative to hydrogen. Hydrogen means when that substrate is unsubstituted. This may be obtained by comparison of delta G for dissociation constant of substituted benzoic acid that of unsubstituted benzoic acid. So substituent effect can be given as minus delta Gx plus delta Gh. So this is delta G for substituted substrate, whereas this is the value of delta G for unsubstituted substrate, and this is related to this log Kx minus log Kh. Again this dissociation constant Kx is for substituted substrate and Kh is for unsubstituted substrate. So likewise log of Kx divided by Kh is equal to sigma x, where this is the substituent constant for unsubstituted substrate. And electron withdrawing groups, they will have the positive value of sigma, that is substituent constant, whereas electron donating groups, they will show a negative value of sigma. So this equation we have already seen the value of log Ka for different substituents. Ka here means Kx. A is acidity. So in case of benzoic acid, when it is substituted, then this is the value of Kx. In our case, say in case of unsubstituted, the value of log Ka unsubstituted is Kh. Kh is 4.20, and this is value for Kx. So this minus this comes out to be 4.20 minus 4, this comes out to be when we add these this comes out to be plus 0.2. So similarly, this is the value for unsubstituted, these are the values for substituted. These are electron leasing groups, these are electron withdrawing groups. So from these values we can calculate the value of substituent constant for each type of benzoic acid which is substituted. So in case of para-nitrobenzoic acid, for example, this minus this plus this comes out to be plus 0.75. So you can see that for lambda for sigma x value for electron withdrawing groups is positive in all the cases and negative in all the cases where the substituent is electron donating. So methyl is electron donating, methoxy is electron donating, they have negative values for this sigma x. Then sigma Hammett substituent constant or substituent constant, this is defined as the collective measure of the total electronic effects, that is resonance effects and inductive effects of a substituents. So whatsoever amount of total electronic effects they are there in the substrate, depending upon the type of substituent, that is called as substituent constant. So basically this is the ability of electron withdrawing or electron donating of the substituent to whether supply or withdraw to or from the reaction site is known as substituent constant. So if ability of electron withdrawing, that means this will withdraw electron density from the reaction site. If it is electron donating, then it will supply electron density to the reaction site. And then substituent constant is independent of the nature of the reaction site. That means this is the reaction site where reaction is taking place, aromatic ring and the carbonyl. So substituent constant will be independent of the type of reaction site we are having. This is dependent only on the type of substituent which is present, whether electron withdrawing or electron releasing. And substituent constants, they are defined separately for meta and para positions. For meta substituent, this is called as sigma m. For para substituent, this is called as sigma p. And as there are two types of effects in the electronic effects, inductive and resonance. In case of inductive, because they are caused by polarization of sigma bonds, so sigma, the value of sigma m, that is meta position, will be more than sigma p for a given substituent. Reason is that we know that inductive effect depends on the proximity of the different groups to the reaction site. So here this X group, which is a substituent, is away from this reaction site by 1, 2, 3 and 4 carbons, whereas in meta position this is away from the reaction site, that is carbonyl, by 1, 2 and 3 position. So that means if we compare the proximity of the substituent to the reaction site, this is away 4 carbons away, this is 3 carbons away from the reaction site. So that is why the value of sigma m is more than sigma p for a given substituent, because here this is in close proximity with the reaction site as compared to para position. Similarly, if we take the case of resonance effect, in case of resonance effect, conjugation is the stronger parameter for para substituent in comparison to meta substituent. So that is why the value of sigma p will be more than sigma m for a given constituent when we determine the resonance effect. So you can see over here when the substituent is present at para position, there is a strong conjugation up to the carbonyl group, which is the reaction site, whereas when we see the meta position, here the conjugation is within the aromatic ring only. This conjugation does not extend to the carbonyl group, which is the reaction site. So that is why the value of sigma p for the resonance effect is more as compared to meta position. Then the plot of log of kx upon kh, which is Hemet equation, this gives us the value of sigma x, this substituent constant for the hydrolysis of substituted ethyl benzoate, this shows a straight line passing through the origin, and you can see over here these are the values for electron leasing groups. This is the value for unsubstituted ethyl benzoate, whereas these are the values for electron withdrawing groups. This is metacyno, paracyno, metanitro, paranitro, whereas this is metamethyl, paramethyl and paramethoxy. So you can see over here that the value of these sigma x, they can be determined quantitatively from this equation, and the slope of this straight line is called as reaction constant or rho. So we can determine the slope of we can determine the reaction constant from this plot also, whereas the value of slope will give us the value of reaction constant, that is rho. So as I have told you, the slope of Hammet plot, that is log kx upon kh versus substituent constant, is gives us the value of reaction constant, and it is meyer of efficiency with which the various substituent transmit their electronic effect to the reaction site. So this has a specific value for a given reaction. So the value for a particular reaction carried out under specific conditions, this remains constant irrespective of the type of whether there is meta substituent or para substituent present in the compound, but in the given reaction that value of reaction constant will remain constant. So the value will be positive in case of electron withdrawing groups, and it will be negative in case of electron donating groups. So under different conditions, when the value of rho, that is reaction constant, is more than 1, the reaction will be more sensitive to substituent effects than benzoic acid. Benzoic acid means unsubstituted acid. And when the value of rho lies between 0 and 1, the reaction is less sensitive to substituent effects than benzoic acid. And when value is approximately equal to 1, then reaction shows no substituent effects in comparison to benzoic acid. And when value of rho is negative, that means the reaction is creating negative charge in the transition state of the rate determining step. So these conditions, they will define that what will be the value of this rho, whether this will be positive or this will be negative. Now as I have told you, there is a linear free energy relationship which is shown by the Hammet equation. This can be demonstrated from the following equations. For example, if this is the rate equation for any reaction where we are having X as the substituent, then delta G is equal to minus RT ln Kx, where this is the value for dissociation constant with substituent X, and the same equation for unsubstituted case, then this will be Kh. And as we know that Hammet equation is log Kx minus log Kh is equal to sigma rho. So by substituting these values, we can have this equation, delta G upon this goes to this place, 2.3 RT plus this divided by RT is equal to rho P. So sigma P and from here we can calculate the value for delta G in case of a reaction where we are having X substituent. So on the basis of this we can see that for a given reaction under a given condition, this is constant, sigma R is constant, gas constant, T temperature is constant, and the value for GH, this is also constant. So that means this has a linear relationship with delta G. Free energy change has a linear relationship with sigma because all these values, all other values, they are constant in nature. So these are the references which have been used, some references from internet, and organic reaction mechanism by Jerry March. Thank you very much.